say a bug landed here on the screen, and it walked around forming this plane curve. Now, if you didn't see the bug, if you didn't see where it landed, you were just given this graph. Would you know where the bug landed? Where the bug is at a certain point? How fast the bug is moving? Or whether it's speeding up or slowing down? Well, no, we wouldn't know any of these things by just seeing this graph. Now, let me ask you, is this curve even a function? Well, let's find out. Does it pass the vertical line test? No, it doesn't. You see, this vertical line hits the curve at 2 different points. That means it does not pass the vertical line test. This curve isn't even a function. Now, this bug doesn't respect mathematics. So since this curve C does not pass the vertical line test, we cannot express y as a function of x. All right? We cannot express y as a function of x simply because it's not a function. So here is where we run into some problems with always defining plane curves in terms of x and y. First of all, many times plane curves, like in this instance, are an even functions. So we can't define them in terms of x and y. Also, many times plane curves cannot be explicitly defined in terms of a single variable. And I'll explain what that means in just a little bit. Also, defining a plane curve in terms of x and y doesn't tell us where the object is at a given time. So we don't know 3 seconds into this bug's travel, into this bug's journey, where he is or where the bug is here on this graph. We don't know. And also, there's no direction. We don't know where the bug started off and what direction it started walking in. So what you've been doing so far in your mathematical journey have been Cartesian equations. Now, you might not know them by that name because we usually don't use that terminology, but these are equations that relate x and y to each other using an equal sign. So you might have a curve in Cartesian equations, say this curve right over here. Let's call it f of x. All this curve tells you here in Cartesian form is the location the object will be along the path. So we know that at 4, let's say at 2, 4, we're going to be approximately at this point right over here, right? So it doesn't tell us when the object is at that point, how fast the object is moving, or whether it's speeding up, it's slowing down. It doesn't tell us any of that. None of that can be described because motion is a function of time. So we now need to introduce a time element. And that's what a parametric equation does. So let me delete this Cartesian equation. Since curve C over here doesn't pass the vertical line test, and it can't be defined as a function of x, what we will have to do is describe the motion of x and the motion of y separately in 2 different functions. And then we'll combine them in order to determine a point here on the curve. Now, this is allowing us to describe a curve that we otherwise couldn't have normally described using y as a function of x. All right, so we would have something like x of t and y of t. Now, t over here is our parameter. Now, in this instance, it's time, but a parameter can be something different. It can be theta, it can be different things. So t is our parameter, and these are parametric equations. So if x is a function of t, we would have something like x of t equals t times 5 minus t, and then y of t equals, let's say, 2t. Now let's go ahead and plug in a value for t. Let's make t equal 1. So t equals 1, all right? So we would have x of 1 equals 1 times 5 minus 1. And then we have y of 1, which will equal 2 times 1. All right, 5 minus 1 is 4, times 1 is just 4. 2 times 1 is just 2. All right, so we would have an ordered pair, which would be 4, comma, 2. Remember, the x values always go first, then the y values. So now we know at 1 second, or whatever time it is, time can be 1 hour, 1 day, whatever, but let's say 1 second. 1 second into this bug's travels, into this bug's journey, we're at the point 4, 2. So we're at the point 4 right here, 2. Approximately right there. This is time equals 1. So we know that 1 second into the bug's journey, it's traveled to this point for 2. If we want to describe where x is and where y is, if we want to describe a point, we can still do it, but we have to do it differently than we've been doing it before with Cartesian equations. Instead of describing y as a function of x or x as a function of y, we can have x and y as a function of a different variable, an independent variable, which will be our parameter. So instead of saying plug in x as you get y's, we say plug in t's and you get both x's and y's. All right, so now let's try time equals 2. All right, time equals 2. We would have x of 2 equals 2 times 5 minus 2. And then y of 2 would be 2 times 2. 5 minus 2 is 3, times 2 is 6. 2 times 2 just equals 4. And now we would have this new point, 6, 4. Now we know that 2 seconds into this bug's journey, we're at point 6, 4. So let's go ahead and graph that. We're at point 6, approximately around here, 4. We're approximately right there. So this right over here is time equals 2. So now we know that the bug has been traveling since here. He came over here at time equals 1, and now 1 more second into his journey, he's right over here. One of the main reasons we want to start looking at parametric equations is that we want to describe motion. And remember, motion is a function of time. So now we know, hey, the bug has been traveling in this direction. Now, since time only goes in one direction, we have to give this curve now a direction, because the bug is traveling in this direction, right? As time increases, he's traveling in this. We indicated it by adding some arrows, all right? These arrows indicate a direction. So by using t's, we not only get the path of the object, right? Because this green line, this C curve, that's the path of the object. But we not only get that, but we also know exactly where the object is each moment along the path, right? We can put in half a second or 0.0001 and see how in tiny increments of time this bug travels. This then allows us to calculate things like velocity or acceleration or other motion related quantities, right? Now you might say in calculus 1 we already did velocity and acceleration. So why do we need parametric equations? In calculus 1, objects were moving only horizontally or only vertically. For example, when we threw an object straight in the air and we had to fall back down, you looked at y as a function of t. For horizontal movement, you looked at x as a function of t. So we were already doing parametric equations, just 1D parametric equations. So now what we're going to do is we're going to combine the horizontal and the vertical motion to get a 2D picture. All right, and that's what we have here in parametric equations, a 2D picture. Now in multivariable calculus, when you move into 3-dimensional space, you can describe 3D motion by simply adding a third equation for the z coordinate. But that's beyond what this is. So parametric equations is just 2D. So now as a recap and a review of everything we've learned today, we have to describe x and y independently because we are not able to graph y as a function of x. It allows us to describe this curve that we otherwise couldn't have normally described using y as a function of x, because this curve is not a function, so we have to describe it using new tools. Now, if we want to describe where x is and where y is, so essentially a point on this curve, we have to do it differently than we've been doing it before. Instead of describing y as a function of x, or x as a function of y, we can have x and y as a function of a third different independent variable, which will be our parameter. This is how we describe a curve when we can't define that plane curve in terms of x's and y's. We use a third independent parameter, hence the name parametric equations. So I hope this video was helpful. If you have any questions, leave them in the comments below. I will get to them and address them. And as always, stay positive.